Hello, welcome to this video lecture on potential flow theory. This is a continuation of a set of video lectures on linear hydroelasticity of ocean structures. These lectures were originally delivered in a PhD summer school in ocean engineering that was held in Harbin, China in July 2019. Before getting started, I'd like to thank Professor Riggs for organizing and hosting these video lectures. This lecture on potential flow theory is an overview of the subject. Those of you interested are highly encouraged to look into references, some of which are listed at the end of these slides for more details. The content of these slides are mainly based on the lecture notes of my PhD supervisor in University of Hawaii, Professor Ertekin. I'm a lecturer in marine hydrodynamics and ocean engineering at the University of Dundee in Scotland. Those of you interested in learning more about the PhD summer school can look at my website, which is shown here. Let's get started. Let us assume the problem of wave interaction with a floating body, and in this example that I'm showing here is a floating offshore wind turbine. The structure in this case is hosting 3 wind turbines and is connected to mooring lines, which keeps it in place. In general, the structure could be of an arbitrary shape and size, and various functionality could be considered for the structure. Here we are interested in learning the impact of waves and current in general on this structure, ocean structure. And answering these questions basically, what is the motion of the structure? We can have 3 translational motion and 3 rotational motions due to the wave loads and current load. And also we're interested in general in assessing the integrity of the structure and determining its deformation. That's where elasticity or hydroelasticity comes to play, and it's covered within the lectures of Professor Riggs. Here I'm going to assume that the structure is rigid for this part and look into determining the motion of the structure. Same concept applies when the structure is elastic. In order to determine the motion, we need to solve Newton's second law. That is, sum of all forces should be equal to mass of the object of the floating body times its acceleration. Now question is, what are these forces and how do we determine these forces? In order to find these forces, especially the forces that are associated to the fluid part, we need to understand the fluid motion. We need to determine the fluid deformation and motion under the wave action. In general, one can separate the fluid deformations into 4 categories, namely translational, where the fluid motions move like a rigid body from one point to the other; rotational motion, where the fluid elements rotate around the vertical axis that passes through the object; and extensional strain, or dilatation and shear strain, where the fluid element deforms its shape and its volume as it propagates from one point to the other. Over the next few slides, we will learn that actually it is very complex if we want to consider the fluid motion under all categories that are listed here. And we will make assumptions to simplify the problem further. If we assume that the fluid is homogeneous and Newtonian, that is, the rate of strain is proportional to stress, then we can write the stress in this form, tau ij being equal to minus p delta ij, and the terms related to the viscosity. And this is pressure and normal stress in a sense. In this case, I'm writing velocity as u1 e1 plus u2 e2 plus u3 e3. And u1, u2, u3 are the velocity components, and e1, e2, or e3 are the unit normal vectors in a 3-dimensional Cartesian coordinate system. Throughout the slides, I'll be using I and J as 1, 2, 3, again for a three-dimensional coordinate system. And I'll also use Einstein summation, where indices after comma, subscripts after comma, denote differentiation with respect to the indicated variables. In this form, that is when we write the stresses and strains, the number of unknowns are more than number of equations, and we cannot solve the system of equations. So we use, instead of this, we use the conservation laws. We start with conservation of mass. Let us consider a material volume of fluid, V of t, an arbitrary material volume of fluid, which is a volume that contains same particles throughout the time. Mass of this volume is defined as integral over volume of rho dV, where rho is the density of the material volume of the fluid. Conservation of mass implies that material derivative or total derivative d over dt, capital D, of m should be equal to 0. That is, when the motion occurs, during the motion, mass is not generated nor is lost. So d dt of this integral should be equal to 0. We can use the Reynolds transport theorem to take this d over dt to the right-hand side of the integral, and we arrive to this equation. Now we consider this Vt the material volume, an arbitrary volume of fluid particles, and therefore this equation should be valid whenever in time and wherever in the space. The only way that this is correct is that the integrand is equal to 0 at all time and for all fluid particles. That is, this equation will be valid for mass to be conserved. We can rearrange this equation and write it in this form, and this is the expression for conservation of mass. Now, so if we eliminate in this point one of the motions, that is, we assume there is no volume dilatation, the fluid or the flow will be called incompressible, and that is the same as saying d rho dt is equal to 0. Substituting this condition into this equation will give us an equation uj comma j is equal to 0, which is also known as the continuity equation. Again, note that I'm using Einstein summation here. So this is actually du1 dx1 plus du2 dx2 plus du3 dx3. It's equal to 0. Now, continuity equation on its own is not sufficient for us to get the motion, because now we have one equation and three unknowns, which are the three velocities. So we look into conservation of momentum as well. And we write the conservation of momentum for the material volume Vt as discussed before. So on the left-hand side, we have d of dt of rho ui dv over the material volume. And on the right-hand side, we have the stresses, integral over the surface for stresses and integral over volume of all body forces, which in this case, for the most part, is the weight of the fluid elements. We can use Gauss's divergence theorem and transfer the integral from the surface into volume and write the right-hand side in this form. And we can again use Reynolds transport theorem to take the material derivative from the left-hand side of the integral onto the right-hand side. So we will have this equation. This is the left-hand side of the conservation of momentum equation, and this is the right-hand side. Same as before, we wrote this equation for an arbitrary material volume, arbitrary group of fluid particles. And here the only way that this could be correct at all times in space is that if the integrand of the left-hand side is equal to the integrand of right-hand side. That is, if we have this equation. We can rearrange the terms or rewrite the terms, and then this is the equation that we find from the conservation of momentum, or in an expanded version, we can have this equation, which is known as the Navier-Stokes equation. a set of partial differential equations that are second order, and they are nonlinear because they have the unknown and its derivative multiplied by each other. Now, I should mention that this approach that we used here is called continuum approach, that is, we're not talking about particles, individual particles. We're talking about velocity and density being continuous over space. And this is a branch of fluid mechanics that separates itself from what I'll be discussing in the next few slides and in solving these equations. In general, we should be able to solve this system of equation because we have 3 equations for momentum equation and 1 equation continuity, so 4 equations in total, and we have 4 unknowns in general, that is the 3 velocities and 1 pressure. In practice, however, except for very simple and basic problems, there is no analytical solution to this problem, to this set of equations. Mainly because of 2 reasons. One is the convective accelerations that are on the left-hand side of this equation. And the other is the effect of viscosity, the last term of these equations, that involve some other unknowns, as we will see in the next slide. That eliminates the possibility or prevents us from solving this equation analytically. In order to simplify this equation, we need to look into a little bit more of effect of viscosity, for example. Here we're looking at a flow passing a body, in this case is a sphere, a bluff body. And as we go from top to bottom and left to right, the flow velocity is increasing, or the Reynolds number is increasing. We can see as near the boundary between the body and the fluid particles do slow down. They because of the effect of the boundary, fluid particles on the boundary move with the same velocity as the boundary itself. So there will be a layer near the boundary which is called boundary layer, and that's where the fluid particles move slower than the ambient flow. As the flow velocity increases, there will be a separation point, which is hard to see in these figures taken from the fluid dynamics of Bachelor. And at that point, velocity is tangent to the normal of the surface. And then if Reynolds number increases, we will have vortices formed, and that's a balance between inertia actually and viscous terms that create these vorticities. And if Reynolds number increase even to a larger value, there will be instability, and these vortices cannot be held in place, and they start shedding, separating from the object, and create the vortex streets and the wake region. Now, all these effects are related or are due to the viscous effects on the fluid. So if we could assume that outside of this region, viscosity does not play a role for us, which is actually a typical case for most of the ocean engineering problems, the type of problem that I mentioned earlier, then we can assume that the fluid is inviscid. And along with the assumption of incompressibility and homogeneous fluid, we will arrive to what we refer to as ideal fluid. So the ideal fluid is driven by or solved by Euler's equation, which is identical to Navier-Stokes equation, with the difference that the last term on the right-hand side of the momentum equation is eliminated, the viscous terms. So here F is the body forces, is limited to the body forces. Now, at this stage, we still have the problem of solving the convective acceleration, the nonlinear term on the left-hand side. and we can make one extra assumption to simplify the problem. Vorticity is defined as the curl of velocity in general, and it's written this way. So curl of velocity, we could write it as the magnitude of these vectors, which is the gradient operator and velocity vector, and the sign between these two. Notice that this is a pure mathematical description of a physical phenomena. So there is no physical meaning for this vector, but mathematically we can write it this way. Now, if we assume that the flow is irrotational, that is, we eliminate one of the other motions that I discussed earlier, then curl of velocity is going to be 0. Now, from here, from this equation, in order for this to be true for all fluid motions and all times, that means that this vector and this vector must be parallel to each other. That is, theta should be equal to 0 or pi or 2 pi integers times pi. They don't have to be equal, they don't have to be in the same direction, they just need to be parallel to each other. So that means we can write one of them as the other times a scalar, times an unknown value, phi, for example. So v is equal nabla times phi. Notice that we could also write this v being equal to minus nabla phi. So that would make no difference, but we are going to move forward with the plus sign, where phi is a scalar. Therefore, we can write u1 as d phi dx1, u2 as d phi dx2, and u3 as d phi dx3. We call this phi velocity potential. And if we substitute now this d phi dx1, d phi dx2, and d phi dx3 instead of u1, u2, u3 respectively in continuity equation, then we will get into this equation, which in expanded form is shown here and known as the Laplace's equation. This is a huge improvement compared to where we started from, in that now we have a linear equation, and instead of 3 unknowns, we now have 1 unknown, which is phi. If we know phi, we can find u1, u2, u3, or velocity field. If we are interested in knowing the pressure, we can substitute this phi into Navier-Stokes equation in general, or Euler's equation, doesn't matter. And we will arrive at this equation, which is known as Euler's integral. So by knowing phi, we can find velocity field, and by substituting into Euler's integral, we can find pressure. This is a very huge improvement compared to the Navier-Stokes equation. Of course, under restriction of some extra assumptions that we made, that is, the fluid is inviscid and the flow is irrotational. Now, this is the domain equations, and this is subject to the boundary conditions. On the free surface, we will have the free surface boundary conditions that are the kinematic free surface boundary condition and dynamic free surface boundary condition. The kinematic free surface boundary condition ensures that particles on the surface move with the surface. That is, they don't jump out of the free surface. And one can write it in this way, where eta is a specifying or free surface. And the dynamic boundary condition ensures that there is a continuous pressure on the top surface that we are defining. Here we have a problem now, and that is we simplified the domain equation, but on the boundary we have two issues. That is, one is that the boundary conditions are nonlinear. We have terms like this. And two is that we're writing these boundary conditions on a surface eta which is unknown. We don't know the surface yet. And that's where linear wave theory comes to play. And it is beyond the scope of these lectures to discuss the linear theory, and it can be found, information about it can be found in references that are discussed at the end of these lectures. But linear theory assumes basically that waves are small amplitude. Therefore, nonlinear terms can be eliminated because they're very small, and the boundary condition can be written for x2 equal to 0 for a surface that is similar to the still water level, same as the still water level. So we eliminate these problems. Now, when it comes to the presence of the object, if the object is fixed on the boundary between the fluid and the body, we would have no flux boundary condition. d phi dn would be equal to 0. And if the object, the body, is floating, we would have d phi dn is equal q dot n, where q is the velocity of the body. That is, particles on the boundary move with the same velocity as the boundary itself. On the seafloor, in this case, located at -h from the still water level, we have again no flux boundary condition. That is, d phi dn is equal to 0. So in classical linear diffraction theory, we have this approach that we separate the total potential into a series of potentials. In the case of a fixed body, we split it into incoming potential, phi I, and diffraction potential. That is, we split the domain, the velocity potential, in the case of when there is no object, or when the object is transparent, and that would be phi I, the incoming waves, the incoming potential, and the potential due to the presence of the object. We modify the field, the object which is fixed, and that is the diffraction potential. And because our governing equation is linear, Laplace's equation, we can linearly add these potentials together, and the solution of these, assuming each of these are a solution of Laplace's equation, the sum of them will also be a solution to Laplace's equation. Now, if the object is floating, we will have one extra category of potentials, and that is due to the motion of the object, waves are generated and they radiate away from the object, and we call them radiation potential. So we can write the total potential as sigma of 0 to 7, where 0 is phi I, incoming potential, 7 is diffraction potential, and 1 to 6 are the radiation potential for the 6 degrees of freedom, 3 translational and 3 rotational. We can write this potential as in this form. That is, we assume the motion is harmonic, and it could be written as e to the power I omega t, where omega is the frequency of the waves. Notice that we could also write it as e to the power minus I omega t. It makes no difference in principle, and the approach will remain the same. Now let's go back again into the question that we raised earlier. That is, we have a floating body of an arbitrary shape. It's connected to mooring lines in this case, and we have wave actions on it. And we were interested in learning what are these forces, what is the sum of forces that are acting on the fluid. And we just learned that we can use velocity potential in describing the flow field. So let's link it now into finding these forces. Let's define capital X of t as the motion, the vector that describes the motion of the structure, which has 6 components, x1, x2, x3, 4, 5, 6. The linear equation of motion of the object, therefore, can be written in this form, where m is the mass matrix of the object, that includes mass and inertia in general, and ks is the mooring effect of the moorings on the structure, and kf is the hydrostatic forces on the structure. And to the right hand side we have f of t, due to the fluid, basically forces due to the fluid on the structure in the general form. We still don't know exactly what this force is. In frequency domain, let's assume that this force can be written in harmonic form, where omega is again the wave frequency, and the displacement also xj can be written as an amplitude times e to the power I omega t, which it actually has a real and imaginary part in it, this amplitude. So if we substitute this into this equation, we arrive to this equation that describes the linear equation of motion of the body. So let's define this R as x1, x2, x3 in general for the fluid domain, and we are assuming that the structure is partially submerged in an incompressible and inviscid fluid, and it undergoes an irrotational the impact of an irrotational flow. If we assume that the structural motion are small, we can write the total phi of r and t in this form: phi I plus phi d plus phi r, which we saw earlier, times a harmonic motion, where phi r are the radiations potentials. Therefore, we create this system of equation, which the domain equation is Laplace's equation, subject to this time linearized free surface boundary conditions, combined kinematic and dynamic free surface, and the no flux boundary condition on the seafloor. It could be deep water, or it could be x2 going to minus h in general. In addition, on the boundary, we have this condition where the diffraction and incoming potential should satisfy, and also the radiation potential should satisfy this condition. That is d phi r dn is equal nj, which nj is the unit velocity of the body in its j's motion. Notice that in general, one could write this for the displacement instead of the velocities, and that is basically how it's done in hydrant. It makes no difference in our solution approach. We can solve this system of equation by use of the green function method. That is, we write phi r in the form of this integral, and the solution, the green function solution of this, is given in several references. For example, in the surface waves of Weyhausen and Leighton, or in marine hydrodynamics of Newman. There are various solutions. I believe this is how it's used in hydrant. This is the green function that is used in hydrant. And by solving this system, we can find this phi r. That solution is actually in hydrant is obtained through distribution of panels, and in general you can consider defining singularities, sources and sinks, and distributing them, or using the panel method as is used in hydrant. And further discussion about that is beyond the scope of this presentation. I suggest to interested readers to look into references that discuss that method. Once phi is known, phi total, we can substitute it back into the Euler's integral that we discussed earlier, and the linearized form of it, and therefore we can find this total pressure in this form. Integrating the pressure around the body, of course, it will give us the total force, which has components in all three Cartesian coordinate directions. So now let's summarize all the forces that we have and look at them one more time. We have the hydrostatic forces, Fsi, which is related to the hydrostatic, the buoyancy effect and hydrostatic forces on the object. We have the wave exciting forces, which are due to the incoming and diffraction potentials, and integral over the surface of this. And we have the radiation forces, or sometimes referred to as hydrodynamic forces, that is due to the added mass, the mass that is accelerating due to the motion of the object, and due to the wave generating or wave the waves that are generated due to the motion of the structure, which we refer to it as wave damping and added mass. So once we integrate all of these into the linear equation of motion, that is, once we substitute this into this equation, we would have this for FTI, and that's the total forces, which is basically, we can rearrange it to appear this way, and is basically the added mass of the fluid and the mass matrix of the object times acceleration of the body plus the wave damping times velocity and the restoring coefficients due to the hydrostatic restoring and the mooring lines. And this is all equal to the wave exciting forces times A, where A is the amplitude of the waves. If we substitute xj in this form into this equation, we will arrive to this set of equations, which is actually a matrix form of equation, where the equation is given in the form of a transfer function. So it's we're writing the equation in terms of the amplitude of the motion, which again has real and imaginary part, divided by wave amplitude. So we can solve this equation by a matrix solver, for example, and find the displacement and velocity, therefore an acceleration of the object. This is called transfer function. Sometimes the square of it, sometimes itself, is called response amplitude operators, or RAO, which has application when we are studying the effect of irregular waves on motion of structures. Now I'd like to show with this system of equation we can look at let me see if I can show it here. We can look at the motions of the structure. We can solve the system of equations, and this is exactly the structure that I was showing, and is solved using hydran with the same principle as it was discussed. We have, in this case, linear waves, and there are regular approaching the structure from an arbitrary angle, and we are discussing, or we are learning about the motion of the structure in general. This concludes my lecture on velocity potential or potential theory. These are a list of references that I mentioned. I encourage those who are interested to look into and learn more about this theory. I hope you have enjoyed it, and continue on with the series of lectures on linear hydroelasticity. Thank you very much.